Section 4.2, Exponential Functions and their Applications. An exponential function is in the form y equals b to the power of x, where b is the base and x is the exponent. The base must be bigger than 0 and not equal to 1. Here are some examples. Y equals 2 to the x, or y equals a third to the x. To evaluate an exponential function, you plug in a value for x and simplify, using a calculator if necessary. Here's an example. Suppose f of x is 4 to the x, and we want to evaluate f at 3, negative 2, and the square root of 2. F of 3 is 4 to the third power. That's equal to 4 times 4 times 4, which is 16 times 4, which is 64. F of negative 2 is 4 to the negative 2. As you recall, negative exponents are resolved by taking 1 over the base to the positive exponent. So 4 to the negative 2 is equal to 1 over 4 to the positive 2, which is 1 over 16. F of the square root of 2 is 4 to the square root of 2. We evaluate this with a calculator. Just put 4 to the square root of 2 in your calculator, and you'll get 7.10299331 approximately. Let's look at the graphs of exponential functions. To graph an exponential function, you make a table of ordered pairs, plot the points, and connect with a smooth curve. Here are some examples. If f is 3 to the x, we have a graph that looks like this. Note, if the base is bigger than 1, it's going to increase over time. Since when you multiply a number by itself that's bigger than 1, it gets bigger. Here we have the graph of 1/3 to the x. Note it goes down because when you multiply a third times a third, you get something smaller. So when the base is a number less than 1 but bigger than 0, you get a decreasing function. Here's some properties of b to the x. The function is 1 to 1. The domain goes from negative infinity to positive infinity. The range is from 0 to infinity. The graph is a smooth curve. The y-intercept is 0, 1, and it passes through the point 1, b. b to the x will never equal 0 and never be negative. If b is greater than 1, the graph rises rapidly. If b is between 0 and 1, the graph decreases rapidly. Translations can also be used to graph exponential functions. Let's explain how to use the graph of 3/4 to the x to produce the graph of 3/4 to the x plus 2 and 3/4 to the x plus 2. 3/4 to the x plus 2. You shift 3/4 to the x up 2. For 3/4 to the x plus 2, you shift 3/4 to the x left 2. We covered translations in a previous section. The natural exponential function. E is a constant, which is approximately 2.718288183. Your calculator should have a button for it. The natural exponential function is e to the x. It comes up often enough that your calculator may have a button that is e to the x. Let's calculate e to the x for x equals 5 and x equals 2.3. So f of 5 is equal to e to the 5th power, which is e to the power 5, approximately 148.41315910257. F of 2.3, that's e to the 2.3. We'll again use our calculator. That's e to the power 2.3, and we get 9.974182454814, for instance. The natural exponential function is used in many applications. Here's an example. The monthly income, I in dollars, from a new product is given by 24,000 minus 22,000 times e to the negative 0.005t, where t is the time in months since the product was first put in the market. What was the monthly income after the 10th month and after the 100th month? Here we're being asked for what is I of 10 and what is I of 100. I of 10 is 24,000 minus 22,000 times e to the negative 0.005 times 10. To get this, you just plug it into your calculator, and you'll get 3,072.95. For I to the 100, you do the same thing, except you plug in 100. 24,000 minus 22,000 times e to the negative 0.005 times 100. If you plug that into your calculator, you should get 10,656.33 about.